Swayam Prabha. Digital India. Educated India.
Hello, Namaste. Welcome back to the course Geographic Information System. Today's lecture is the continuation of the previous lecture, previous two lectures, where we have looked at different data models. The first thing that we looked previously was how do we do a digital terrain model. Okay, so when I say digital terrain model, it represents the terrain surface of the earth area. So that is what we looked at, what is a digital terrain model. Then we translated into digital surface model, which is actually representing anything on the surface. When you overlay all the things on the surface to the digital terrain model, then it is called as a digital surface model. Then we looked at digital terrain model is a 2.5D representation, whereas digital terrain model is a 3D representation. Digital elevation model is a 3D representation. I am sorry about that. So once we have looked at that model, then we looked at the grid model. Grid model, we clearly understood that it is each grid that is formed is a collection of cells, and every cell is an approximation of the region that is below to a point. So which means to say it has only one value and it does not give a varied value across that particular cell. So now how do we represent this particular thing is by the gridded representation. That is what we have looked at the previous class. In today's class, we would be translating into understanding the triangular irregular network, irregulated network or irregular network. So this is one kind of modeling, a model very well known in kind of representations of such datas. Then other model that is very well known and people have used it, most of you have come across it in one or the other forms, is nothing but isolines. We look at isolines, we look at triangular irregulated network, then we would look at accuracy. Why accuracy is important and what are the factors that is affecting the accuracy. Then finally, there is a thing that we have to understand is representing time. When we are doing a temporal analysis, we have to represent time. How do we represent time? Is there a way to understand and represent time? That is also the thing that we will look at in these slides. And finally, we would look at in this class the models for movable objects. So till now, whatever we are looking at is more of a stationary subject and is quite subjective. But when we are actually modeling the real phenomena that is actually moving, we find a lot of moving objects in the real world. So in order to represent that, do we have a model? Yes, we do have a model that is called a network model. So we will look at network model also in this class, and that would end this class. So first let us get into triangular irregulated network. A triangular irregular network is actually an array of triangular areas. So when I say triangular areas, it is an enclosed polygon, okay, with their corners stationed at selected points of most importance for which elevations are known. Please be careful of this. When I say most important, it does not mean that it is an important place on the earth's surface. It means to say that where we know the values, that point on the earth's surface is selected as a nodal point. So now with this point as a nodal point, we connect the other nodal point which is known. Similarly, the triangles are built with different nodes, and finally that becomes the representation of the earth's surface. Then inclination of a terrain is assumed to be constant in this each triangle. So here also we have an approximation, unlike the grid model. Here we inside a triangle we assume that particular value remains constant. Okay, so that is what is about the triangular irregular network. The area of a triangular may vary, with the smallest representing those areas in which the triangular varies the most. Okay, so Now terrain varies the most, sorry. So when we say when there are terrain values that are actually changing, that is where you have the smallest of the triangles. The largest of the triangles is where you have a least variation in the entire terrain. To construct TIN, all or that it is also called as TIN, it is a tin model. All measured points are built and the model thus representing a line of fracture, single points and random variation in the terrain is developed. So I'll give you some I'll show you some of the methods of how the tin model is built. Tin model can be built using two distinct procedures. One is distance ordering and one is Delaunay triangulations. But when we look at both of these, Delaunay gives triangulation gives you is more advantageous when you are using the triangular irregular networks. So we'll look at why it is advantageous also. But first let us understand how do you do in distance ordering. So how the first thing is compute the distance between all pair of points and sort from the lowest to the highest and connect the closest pair of points. Okay. So for example, I know this point, I know this point, this is another point of variation, this is another point of variation, this is another point, this is another point. So the first thing that I will do is I will calculate all the distance between these points 1, 2, 3, 4, 5, 6, 7. Okay. First thing is I will find out the distance between these points and then sort it from the lowest to the highest. Let us say the distance between these 2 points are the lowest. So I will start connecting the closest pair of points. First I will connect this. So this is assumed to be the second lowest, and once you have we have done this, then we will connect these two different nodes. Okay. Then start connecting the closest pair okay, that do not cross earlier lines. Okay. So only thing you should remember that in this kind of network the line should not cross each other. So we will connect this, then connect these two so that it does not cross. Okay. Repeat this procedure until there is no further lines, that is the lines can be selected in the entire network. Okay. So the points will be now connected with as triangles. This is called a distance ordering. Each triangle is representing a particular set of region where there is absolutely no change in the terrain. So it is representing the terrain values. That's one kind of modeling as far as distance ordering is concerned. There is another way of looking at tin model is Delaunay triangulations. When we look at Delaunay triangulations, it is actually a very proximal method that satisfies the requirement that a circle drawn through the 3 nodes of a triangle will contain no other node. So that is what it has to actually precisely tell you. Once you have drawn the triangle, as I have already spoken to you in the distance ordering, the circle should be drawn in such a way that through the 3 nodes of a triangle and will contain no other node. It has to satisfy this. For example, if I have connected these 3 as 3 nodes, when you draw a circle, it should not cover any other node. So this is one of the very efficient methods that is available when you look at the tin model. So when we look at this, it has several advantages. Okay, but having said this, tin model is also the industry standard developed by specifically with ArcGIS as a software. It has grown over years, and you can see a large number of methods used for such models. And when you look at the advantages, it ensures that any point on the surface is as close as possible to the node. Okay, which means to say that it is actually giving information of every node, every surface and every point on that is being represented. The triangulation is independent of the order the points are processed. So that is what is extremely important. When you look at distance based method, you have the lowest distance first and the highest distance last that is connected, but here we do not have that aspect. Okay. So once we have connected a triangle, okay, so this any 3 nodes that is forming a triangle, draw a circle and say that it does not fall into that particular, there is no node that is falling into the circle. Once this criteria is solved, so the triangular irregular network is actually built upon. Okay. So, the points are established by if I have to define TIN in a very simpler way, the points are established by triangulation and in such a way that no other points are located with each triangle that is converted to circle. That is what I mean by the previous one. So, I have already said what are the different advantages and what the only disadvantage that we find in Delaunay triangulation is analysis involving the comparison with other layers is extremely difficult. So, that makes it aspect really difficult in terms of when we are trying to analyze layer by layer issues that has to be seen in the entire database. Otherwise, it is an excellent method of obtaining a TIN model, and TIN model is considered to be one of the efficient models that is available in industry today. So, I have just given you a representation of this. This was actually adapted from Ian Co, wherein this entire description of this particular image gives you exact way of how a 3D view is developed. First the triangulation is developed, then how the surface is developed, and finally the 3D view is developed. The first thing that we have to understand is break lines. Break lines are linear features which define and control the surface behavior in terms of smoothness and continuity. That is what is called break lines. So, for example, here you have a break line which is actually there are no break lines here, it actually continues all throughout, but when you see in the second image here, so it has a break line. If you see here, so this image has a break line. When you see these are certain break lines, these are soft break lines, whereas these are hard break lines. Okay. So, if you see here there is an, so when we are looking at this one, the hard lines define the distinct breaks in a slope, that is why you need a hard line. So, it actually says where are the distinct values that break in a slope. Okay. Linear interpolation should not occur across these lines. This is what is an added constraint here. There should not be any linear interpolation in the entire set. When you look at soft lines, they do not interrupt the surface smoothness. Soft features are generally have no geometric significance, but are needed in triangulation nonetheless. So, you need soft lines, you need hard lines, but hard lines have a distinct breaks, whereas soft lines do not have a distinct breaks. That is what is the distinction between a hard line and a soft line. So, now we have this data. So, with no break lines, we have soft break lines and we have hard break lines. So, when you look at this, let us say we are actually deriving this triangulation by any one of those methods. Okay. So, once we have done the triangulations here, you can see number of triangles that are representing the same surface on the earth surface, which means elevation remains constant across all. Okay. So, when you have hard break lines, you can look at number of surfaces here. So, once you have done it, the entire surface data is then overlaid on this aspect. Okay. So, once you have done, now you have the plus z values, where plus or minus z values. So, this can be looked at in a 3D view. So, this is what is a representation of this particular 3D view. This is rotated across, this is actually the one that is here has been rotated to the minus 90 degrees, so that you can see this is the way it is represented. So, this is where you have lower points and this is where you have the higher points, that is the plus z values. So, this is how a triangular regulated network is built and then converted into a 3D view. Okay. So, the next method that we would look at is the isolines. Isoline is an imaginary line on the ground joining the points having the same elevation at a specific interval. I hope rather than isolines, you have heard about a specific term called as contours, right. So, contours is also referred to as isolines, lines that show elevation and shape of land in a map. and all of these isolines are joined to the points having the same elevation and do not cross each other. That is the very important part of it. Okay. So, when I say isolines, it is you should understand that these are the points that is actually joining the ground with the same elevation and are also called as contours. So, I have just shown a representation of an isoline. For example, this is your let us say the ocean. Okay. A is representing the ocean. Now, when we draw an imaginary plane, we get the surface at 20 feet. Next, another imaginary plane C is drawn, wherein you get surface at 40 feet. Another imaginary plane is drawn when you get surface at 60 feet. The same is represented into a topographic map, something like this. You have a topographic map here, wherein you have 20, 40, 60. So, this is 60. You can see these lines that are representing never crisscross each other and are representing same elevation on the map. That is why we call it as an isoline. Okay. So, this is how we represent an isoline. So, what we have seen here is isoline interval is 20 feet that we have considered here. Datum is the mean sea level that we have considered. So, and it also gives an idea of height. That is why we use an isoline. Wherever you need the idea of height, you can use an isoline where surface features as well as relative position in the plan is shown. For example, here this is an hillshade map that has been developed from the DM. We will also develop the hillshade map in our practical classes. When we look at this hillshade map, you can see various features on the ground that has been denoted, and when you look at the same in the isoline map, you can see where there is the highest elevation and where there is the lowest elevation. If you see, highest elevation is very close to this point here and lowest elevation is somewhere here. Okay. The same thing is represented here. The highest elevation is here, whereas the lowest elevation is here. And please mind it that no contour crisscrosses each other, no isoline crisscrosses each other. Okay. So, that is a very important point where students make a mistake, that they draw contours in terms of sometimes it crisscrosses each other. Please see that it does not, I mean, that is a wrong way of representation. Now, so these are some of the isoline representation. So, you can see the elevation values have been added here. You can see these are the elevations. So, we have generated a thematic map so that you understand this, and this is a normal isoline representation, and this is in the gray value shades. So, you can see the lighter shades actually representing an elevation that is at a very high elevation, and the ground at a lower elevation is represented in gray, complete gray or closer to black. So, when we look at isolines, they have certain characteristics. One is it is continuous. A series of closed isolines on the map represent a hill if the higher values are inside. Okay. So, keep this in mind when you are actually representing, it has to be understood that as if there is a series of closed isolines, then it is actually representing higher values that are inside. A depression, if higher values are outside, is if the higher values are outside, then it is a depression. So, here when you look at here you have 590, 600, 610 and 620. So, higher value is inside. So, it is actually representing a hill or higher elevated region is represented by this. Whereas, when you look at here 620, 600, 610 and as it goes to the lower elevation. Sorry, this is a decreasing elevation here. So, when you look at this is giving you a depression. Okay. So, it is from a higher elevation to the depression region. Okay. Then spacing of lines. So, there are people who have developed isolines, who have developed contours, but very important point is they forget is how you space a line. A line should be evenly spaced with area of a uniform slope. So that is extremely important. The slope should be extremely uniform. If you draw a line, if you start drawing a line at 20 feet interval as I have shown previously, and suddenly you start looking at the values at 40 feet and then 60 feet, where interval is 60 feet. So then it is not a true representation of the particular surface. That has to be characterized at 20 feet all throughout the model. Okay. Then unevenly spaced areas with variable slope. So if you have a variable slope, then only you have unevenly spaced regions. But when you are looking at isolines, normally the model is always evenly spaced. Only in terms of, for example, when you are looking at certain regions which are completely uneven, every point is actually changing, that is extremely difficult to get. In such cases only then you have isolines representation which is uneven, otherwise it has to be even. Then isolines cross a ridge line or valley line at right angles only. So please keep this in mind. Okay. When you look at other advantages, it furnishes information regarding the features on the ground, whether it is flat, undulating or mountainous. I gave you an example in the previous slide on if the isolines are in increasing fashion, then it is a hill. If it is decreasing fashion, then it is a depression. So similarly, when you have isoline map that furnishes information whether it is flat, undulating or mountainous, that is what I explained in my previous example. From the isoline map, sections may be easily drawn in any directions. So that is another point that you have to look at. Each sections can be understood and drawn in different directions. Intervisibility between two ground points plotted on the map can be ascertained. So this is of use to many applications. So intervisibility of any two ground points can be plotted and ascertained if you have an isoline model. But there are certain disadvantages that people have to look at. So some of them are poor for computer representation. So you do not have any formal digital model which is supporting this. Poorly suited for calculation of elevation values of a new point. Okay, if you are trying to calculate the elevation of unknown new point, then it is quite difficult to understand it. Then must convert to raster or tin for any kind of analysis, otherwise you cannot do any analysis on using an isoline. Then the contour generation from point data requires sophisticated interpolation routines, okay, often with specialized softwares. Nowadays most of the software can handle it. When I say specialized softwares with which are specialized in terms of GIS. So GIS tools and science. So contour generation from point data, so you need specific tools or specific science based tools on geographical information systems, only then you will be able to generate any data from isolines. So any of those freely available software or even your ArcGIS, MapInfo, all of these softwares can generate any from the contours from your point data. So coming to accuracy, the accuracy of the terrain is determined primarily by various issues. One is random variation in a terrain. How random is the variation in that particular terrain? Then the spreading of the measure points. So how has the points been mentioned in the entire model? Is it mentioned as a group in a certain corner, or is it has a random measurement all throughout the place, or it is you have points all throughout your place? For example, let us say that there are only 3 points in the entire region that you are trying to model, and those 3 points are in one nook corner. So what happens? The spatial variation is represented only in that corner, whereas other points will be given the same variation as the last point that you would have looked at. So that is what is the thing that people have to look at. You should have a lot of measured points, so that you know how the spreading has happened, how you have the understanding of the whole terrain. Otherwise you do not know the terrain characteristics at all. Then distance between the measured points. So if it's, as I said, if the distance between the measure points is smaller, then it is a better polygon than having a larger distance polygons in terms of when you are developing a model. Then method of generating the model, grid and triangular surfaces. So, the way it has been developed and the way it has been stored is extremely important. Finally, when you are developing model from a point, you use certain statistical techniques like interpolation. So, interpolation between points in a model, what kind of interpolation has been done? Okay. So, such kind of the things are needed in order to determine the accuracy of the model. Okay. It is not a straightforward answer to say what is accuracy of the model, but you have to look at all of these parameters, for basically these 5 parameters, and there are many more, but these are the things that people have to keep in mind in order to see how accurate the particular model may be. So, I also said that in certain models we have to represent time. So, how do we represent time? In the real world, time plays a very important role where things change. Okay. So, attribute and geometry, these are two things that we see in a topological change of an object with time. Okay. Attributes change. For example, if you are trying to build the database of a roads in Kolkata. So, the attributes of that particular road may vary every 5 years when it is tarred, or when it is whatever the changes that happen in that road or widening of the road happens. So, those are the attributes that change, and along with the change, that the geometry also changes. So, that will change with time, right. So, this has to be incorporated considering the time as an attribute every 5, as I said, every 5 years. So, that becomes an attribute. So, to the object in the same way of as the other attributes. Even so, this particular approach will not create any logical connections between various time layers, but it gives you a meaningful information of how the evolved aspect of time. For example, there is an attribute that has evolved over a period of time, but it does not give you any logical connection. It only says that from this particular time to this particular time, this has evolved over a period of time. So, when you say that such attributes have evolved over a period of time, it gives a meaningful information to anyone who is actually looking at how the real world has translated from one year to the other year. So, that is how we start looking at representing time. And the next thing is, okay, so now till now we have looked at representing a static object, okay, house, road, industries, all of this stuff. But when we have to represent a moving object, that is extremely important in a real world model. Without having a moving object, your model is never built. Okay. For example, if you have vehicles that is moving on the road, so that movement is nothing but has to be captured by your model. Then water running over the terrain surface has to be captured by your model. So, in order to capture this, you need a certain model which can address these issues. So, for accounting this, we have some model called as a network model. So, network model assumes topological data built up of links and nodes. Okay. It is a topological data, as I said previously, that is built up of links and nodes. The model is actually based on 3 relationships. One is the continuous and the connected network. Then you have a rules for displacement in a network. Then the possibility of attribute values accumulation due to displacement. Okay. So, all of these 3 things are built as relations. That is, first is a connected network where the connections are. For example, if you are looking at vehicles and a road, so different connections in this complete network. Then rules for displacement in a network where it can be displaced and which direction if you are considering the vehicle. Then the possibility of attribute value accumulations due to any displacement that is happening. So, this is what we have to look at. But in a network model, movements are limited to the network, but when it comes to a situation where access in the terrain such as water that flows on the surface, okay, you cannot really capture it in a model. So, that fails. So, if you really want to look at something that is looking at how the surface water is actually moving, then you should have a geometry that is represented as a regular cells. If you can represent that movement as a geometry of regular cells and attributes that are represented with the coded values of each cell, then your entire network model can represent even events such as the water flow on the surface. So, that is the thing that we learned. We have a network model, but network model without geometry of representation over a regular cell is representing any of those wherein you are not looking at the surface flow, like the water surface flow. But in case you use if you want to access, you can access about details about the terrain, you have to look at something that is with the geometry and with the regular cells. So, if you have understood the geometry with the regular cells into the model, if you have put all those details into the model, then that model can efficiently model any process, any natural process much efficiently. So, coming to the summary of today's class, we first started with triangular irregular network, wherein we looked at how the tin models are built. There are two types of ways of building a tin model. The first thing is we looked at the distance spaced method, then we also looked at triangulated method. So, those are the two very basic methods of how a tin model is being built. So, we looked at the advantages of the different models and how these models are built. I also gave you an example of how these models are built. Then we looked at isolines. We spoke about how isolines are connected. Isolines are connected based on the same representation values or the same elevations in that region. So, isolines, as I said, should not crisscross each other. Isolines are also called as contours. That is what we have understood. We have also seen how the isolines can be represented. Then we looked at the advantages and disadvantages of isolines. So, we clearly understood that isoline representation, the computation, layer wise computation is extremely difficult, and also we understood that isoline cannot be directly used. Instead, it has to be either converted as a raster or converted into a tin model in order to represent it. And then we looked at accuracy. What are the 5 different ways of looking at accuracy? What are the things that you have to see if you have to look at accuracy? Then we looked at how do we represent time. Time becomes a very integral part when you are looking at certain aspects and certain aspects that are involved in terms of representing any network. Then we looked at models for movable objects. So, these are those models based on networks. We also looked at how network with only topological information cannot actually model the real world phenomena like the surface flow, but if we include terrain, the geometry with the gridded values, then it can even model the movable objects which are on the surface. So, with this we will end today's class. In the next class we would look at more further aspects of how we develop these models and how we interpret these models in today's context. Thank you very much. Let us meet in the next class.